Very good evening to all. Till now, only 25 faculty members are joined. We are waiting for the more faculty members. Anyway, already our resource person is there in our link. So we'll start the session immediately. So before going to start the session, let me introduce today's speaker, Dr. Anuj Sharma. I am Dr. Preetham Kumar Das, Assistant Professor, Department of Mechanical Engineering. I'll take this privilege to introduce about Dr. Anuj Sharma, today's speaker. Dr. Anuj Sharma is an Assistant Professor in the Mechanical Engineering Department at BITS Pilani. He earned his PhD from Wawa Atomic Research Center, Mumbai in 2019, following an MTech in Manufacturing Engineering from SLIT Punjab and a BTech in Mechanical Engineering from Government Engineering College, Sundarnagar, HP. Coming to his research and professional experience, after completing his PhD, Dr. Sharma worked as a senior project scientist at IIT Delhi on DRDO funded project for 1 year. His research focused on investigating shock wave interactions with energy absorbing materials. Then he moved to Cardiff University, UK, where he worked for 2 years as a postdoctoral research associate. His research at Cardiff centered on understanding nanomachining processes using an atomic force microscope setup, with modeling supported by a novel SPS FEM combined techniques. He worked a lot in there. Coming to his publication achievements, Dr. Sharma has published extensively in high-impact peer-reviewed journals, international conferences, and many book chapters. His research primarily focuses on atomic scale simulation, MD simulation using MMPS in nanoscale machining. During his PhD, he conducted extensive experimental studies on ultra-precision diamond turning. His outstanding contributions earned him the prestigious Outstanding Doctoral Students Award in the engineering domain among all the Department of Atomic Energy DA institutes. With his expertise in nanomachining, computational simulation, and advanced manufacturing, Dr. Sharma brings invaluable insights into this FDP. So we all look forward to his engaging and informative sessions. So welcome to the session, sir. Now the session is yours. Please carry on. Thank you.
So, thank you, Preetham sir, for this nice introduction. So I would like to share my screen and then I will start my presentation. So are my slides visible?
Yes, sir. Yes, sir. Visible, sir. Please carry
So
on.
is it movable?
Yeah, movable, sir.
Okay. So thank you for first of all for inviting me for this ATAL FDV program on AI and simulation in additive manufacturing in Aditya University. So
Anuj sir, can you make the PPT, means it is the sharing screen is coming. Next slide is also showing. So can you make the full slide or full screen sharing basis?
Just a minute. So is it not in the slide mode?
No, actually it is showing the next slide option also. It is showing clearly your next slide.
Okay.
What is your next slide? Now your screen is not shared. It's not visible.
Just a minute. So I am sharing the screen and is it full screen now?
Okay, sir. Okay.
Just a minute. I will check again.
I think it's left side, the bottom option is here, sir. Just check it once.
Where?
Left side. Corner.
Okay.
First, that one.
This one.
No, there is a pane slides option. Okay.
Just a minute.
Okay, sir. No problem. Please continue, sir.
Okay. Okay, I shall continue now. So, first of all, I will continue with my academic and professional journey. So, I come from Himachal Pradesh, and I did my BTech in Government Engineering College, Sundarnagar, in mechanical engineering. Then after that, I did my MTech in manufacturing engineering from Slight Longowal, and after that, I joined my PhD in Bhava Atomic Research Center. There I carried out this nanoscale machining, and I used molecular dynamics simulation to carry out the nanoscale machining with some experiments as well. After my finishing my PhD, I joined IIT Delhi, and I worked there as a senior project scientist in one DRDO project where I investigated the shock wave phenomena in the materials. And after that, I did my postdoctoral research in Cardiff University, UK, for 2 years. And then after that, I joined the BITS Pilani. So currently I'm working as assistant of a professor in BITS Pilani. So the agenda of the talk is these various topics will be discussed in this talk. So the first one is the modeling techniques based on various length and time scales. Then atomic scale modeling approach, that is molecular dynamic simulation. After that, I will discuss about nanoscale machining by diamond turning, and then how it will be modeled using molecular dynamics simulation, and then the results of this nanoscale machining on two different materials like copper and copper beryllium will be discussed, and in material removal mechanisms will be discussed in the nanoscale cutting of these materials. And similarly, I will discuss the tool wear and surface generation mechanisms in the nanoscale machining of copper and copper beryllium. So first question is why simulations? So simulations are important because in except for simple cases, there are no analytical solutions available for most of the problem. So in those cases, either we can go for experiment or simulation. But in some cases, experiments are also difficult to carry out because like the case of these shock waves, like blast experiments, these are very difficult to carry out. So there we need some kind of simulation where these experiments either are very expensive or it is dangerous to carry out. So simulations help in these scenarios to understand the phenomena. And also sometimes experiments are expensive with time consuming as well. So there also simulations are very helpful. And sometimes there are too many parameters to control. So that also makes the experiments to study, the studies become difficult. So simulation help in saving the time, money, and also the safety means in some, as I said, that in some experiments, the safety concerns are there. So these concerns are eliminated in the simulations. And simulations are also very powerful tool where they can replace experiments either if any finding is there. So they also tend to provoke the experiments. So that also lead to carry out, motivate us to carry out some experiments. And also sometimes they help in explaining the phenomena which we cannot understand through the experiments, because sometimes these experiments are so fast that we cannot catch the phenomena during these processes. So simulations help in those scenarios very much. And also it is a bridge between the theory and experiment. So because sometimes we have the theory and but experiments are there is a mismatch. So if by simulation we can bridge that gap. So there the simulation are very helpful.
Sir, good evening, sir. Sorry to interrupt.
Okay.
Sir, please put in presentation mode, sir, so that we'll be able to see everything in detail. Like it is not in the presentation mode.
Just as.
So hide presenter view would work, sir.
Sorry?
Hide presenter view, like just click on that.
Is it coming now full screen?
Yes, sir. Fine, sir. Thank you so much.
This is not, yeah. Okay, so coming to molding and simulation based on different time and length scales. So if we see the length scale, so there are different length scales. So it varies from angstrom level to the meter level, some hundreds of meters level. So for very small length scales, there we apply the quantum mechanics, because there we have the these atomic and electronic effects. So we have to use the quantum mechanics approach. But in larger cases, where we see the continuum mechanics or macro scale processes, there we have to use the continuum mechanics approach, like finite element based processes, finite element based approach. So these are two extremes, but in between there is a one mesoscale, and there is one it varies between nanometer to micrometer, where we can apply molecular dynamics simulation approach. So for the quantum, rather than a nanometer length scale, we can use our quantum mechanics approach, which is based on density functional theory. And in this case, from nanometer to micrometer, we can use molecular dynamics simulations. And for these mesoscale, which is in between the molecular dynamics simulation and finite element methods, we can go for phase field methods. And for macro scale, we have to use the finite element method, because there we assume that the materials are continuum in nature. Means we consider the homogeneity in the materials. But in these cases, in the initial two approaches, there are discrete effects, because each atom can behave differently. So materials, we cannot assume the homogeneity. So there is heterogeneous nature which we have to deal. So that can be dealt with our atomic scale approaches. So there are, if it is less than nanometer scale length scale, then we have to go for quantum mechanics approach. And if it is more than, if it is in between nanometer to micrometer, then we have to apply the molecular dynamics simulation approach. So coming to molecular dynamics simulation, so I will cover first the basics of molecular dynamics simulation, then nanoscale machining, and after that I will show my results on how the molecular dynamics simulation has been used for nanoscale machining. So what is molecular dynamics simulation? Basically, it applies the Newton's second law. So for example, if there is an atom, ith atom, so if it is under the influence of external force, so it will have the acceleration, this AI, and here the mass of atom is mi. So under the external influence of external force, this atom will gain the acceleration as AI. And we can use this equation to update our position and velocities of the atom. So I will show you later that how will it be used. So this method, which uses the classical mechanics approach for atomic movement, is known as molecular dynamics simulation. So here we are considering the atoms, but we are not considering the quantum scale effect. So that's why we are going for this classical mechanical approach. So here we are not using the this famous Schrodinger wave equation, because in the quantum mechanics we consider that particle has both wave and particle nature. With the duality is there, but in this molecular dynamics simulation, where classical mechanical approach is there, we consider atom as a particle only. So I have shown in here in the figure that usually in reality, in the atom there is a nucleus, and around the nucleus the electrons revolve. But for this case is feasible in the case of quantum mechanical approach. But we are going for classical mechanical approach, so we will not consider these electrons and nucleus. We will simply consider as atom, which is spherical in nature. And atom to atom interaction, this energy will be provided by some interatomic potential. That's it. We will apply some external potential energy function. So basically, we are neglecting these electrons and nucleus. Only atom is considered, and in the structure there will be other atoms as well. So those interaction between different atoms will be considered by the will be taken into account by the taking into account the interatomic potential equation. So as I said, that approximation that in the classical mechanical approach is atom is considered as a sphere with point mass at the center. So there is no electron we have considered in this approach. Now, as I said that we have to use interatomic potential function. So for example, when atoms come close, so they feel that first the attraction and then the repulsion. So up to certain distance, they will feel the attraction, and after that, if they come more closer, so due to electronic repulsion, they will have some repulsion. So these phenomena are put into some interatomic potential energy function, and that interatomic potential function is provided in between the two atoms. So that cater for these repulsion and attraction usually happen by the electron and nucleus. So basically, we are not considering the electron and nucleus there, just the these energies are considered by this function only. So as I said that I have this force which is under the influence of force, this atom will gain the acceleration, which is nothing but the derivative of the velocity, and which is nothing but the double derivative of the position. So if I integrate it 2 times, so we will get the position. And if we integrate single time, then we will get the velocity. So, but we should have the another expression for the force, so then that we can equate this equation to the force. So there is another equation for the force, that is basically if there is an energy. So if we have we take the negative gradient of that potential energy, then we get the force. So basically we are one is the force between atoms, which is defined by the this interatomic potential energy function. So basically this U is a function of the position of the atoms. So one atom will be surrounded by different atoms. So that energy is stored in this U. So if we take the double derivative as a single derivative with respect to R, the position, we will get the F. So this can be equated to this mass into acceleration. And if we double integrate this acceleration or this expression, then we will get the position, and in single integration, we will get the velocity. So in that way, we get the position and the velocities of the atom, and every time step we update those positions and velocities and acceleration. So in that way, this in the time evolution of atoms happen in the simulation. Now comes the thing that how will we relate the macro scale properties with the micro scale behavior. So in the macro scale variables, we get like volume of the some, if we consider the gas, then volume of the gas, pressure in the gas, or temperature of the gas. But in microscopic approach, we only know the velocities and the position of the atoms inside that gas. So we have to relate these microscopic parameters with the macroscopic variables. So this is the requirement. Then only we can analyze the macro scale processes with the help of microscopic approach. So this requires our statistical mechanical approach, which links the position and velocities of the atom with the macro scale properties like volume, pressure, or temperature. So there comes the famous ergodic hypothesis, which states that the ensemble average or sample average can be used to compute the average values, which can be replaced by time average of the over the simulation. So basically, every macro state has different microstates. So these microstates are sampled by molecular dynamic simulation using the small subset, which is known as entire this thermodynamic ensemble. So with the help of example, I will show you that, for example, if we consider this as a macroscopic system, so it can be divided into different microscopic system. So there can be millions of microscopic system which have the position and velocities of the atoms. So likewise, here I have shown the liquid in a beaker. So this one microstate shows these atoms which has different kind of velocities and position. In the other microstate, there is a different kind of velocities and this position. So these both are means varying differently in these two different microstates. But if we take the macroscopic parameter like temperature of this liquid, so it will be same in both the cases. So it will be same, but the microstates are different. So basically this comes as the average. So average decides the macro scale parameters. But if we see microscopically, so this system is different and this system is different. So ergodic hypothesis states that if we take this average and if we take this system and if we take the summation of this system over time average and this ensemble average will be equal. So this phenomena is used in molecular dynamics simulation, that over time, if we integrate the properties, so that will be equal to our this average, which is the subdivision of this macroscopic system. So basically, the ergodic hypothesis states the long time average is equal to the ensemble average if we approach this time limit to infinite time. So for long time average, it will be equal. The ensemble average will be equal to your time average. So there are various statistical ensemble system which are used in molecular dynamics simulation, like the microcanonical, the canonical, and isothermal isobaric system. So microcanonical is NVE. NVE means number of atoms, volume, and energy will remain constant throughout the simulation. So basically here your energy will be conserved, but temperature can vary. Temperature or pressure can vary. In canonical ensemble, your number of atoms, volume, and temperature will remain constant. So these kind of things are usually studied in endothermic or exothermic reaction. So temperature will remain constant, but your energy can be exchanged between the system and surroundings, and also pressure may vary. And in the third system, this is NPT, where the number of atoms in the system, the pressure and the temperature remains constant. Your volume may vary of the system. So this is close to our laboratory condition where ambient pressure and temperature are usually constant. So these three ensembles can be used for our molecular dynamics simulation. So now the question that comes that what can be done with the molecular dynamics simulation. So our MD can be applied to system containing metallic system, non-metallic system, polymers, biomolecules, any chemical system, any chemistry we can study in this. But the limitation is that we have the length scale of nanometer and time scale varies from nanosecond to microsecond. And atoms we can go for few hundreds to few million. But not very large system can be studied. And phenomena we can study the chemical, mechanical, or physical phenomena we can study over these length scale and time scale. And where MD is suitable, where experiments are not feasible, like if we have to microscopically analyze any system, cutting system, or any mechanical system, then we have to go for molecular dynamics this study. And where the discrete effects are dominant, means your continuum approach is not valid. Your material have many impurities or heterogeneities. So in that case, we cannot consider material as homogeneous in nature. So there we have to apply the molecular dynamics simulation approach. And as I said, that it is applicable for nanometric length scales. So we cannot apply this approach for very large systems like continuum scale problems. Now, what are the steps involved in MD simulation? So first we have to create an initial state. So in initial state, we have to give the initial position and velocities, only the initial position of the atoms in the system. So likewise, if we are studying the like aluminum, so it has FCC structure. So based on FCC structure, it will take the positions of the atoms. So those positions will be considered as the initial position. Then we have only the atomic spheres. We don't have any interaction between them. So we have to apply some interatomic potential energy function so that any repulsion or attraction can be introduced in between these atoms. So we have to introduce some interaction potential functions. So those are sometimes can be bonded or non-bonded. In most of the gaseous problems, those are non-bonded atoms. But in case of our like covalent system, metallic system, there are bonded systems are there. So we have to apply these kind of models in our atomic or molecular systems. And then third, we have to predict how particles move. So that I already discussed that one expression comes from this force is equal to mass into acceleration, and the other expression for the same atom, it comes from the negative gradient of energy, which is nothing but this energy, interatomic potential energy. So these expression can be equated with each other, and we can double integrate them, and we can find the positions and the velocities, and they have to be updated on time, over time. And what are the potential functions? So it can be, as I said, it can be bonded, non-bonded, or any external functions are there. And then we have to apply our, we have to extract the forces in between the atoms by taking the derivative of this potential energy. And the other equation is this force equation. So these have to be equated. And this potential energy can have different interactions, like these type of attraction and repulsion. So for example, these atoms come closer, so there's attraction. First there will be attraction, and then there will be a repulsion. So your energy will become very high if two atoms come very close. So similarly, there can be bonded attraction or charge based. So if there are charges on the atoms, so you have to apply this formulation. You have to add this formulation in the potential energy function. Then similarly, if there are bonds or there are different orientation, there are angles, or there are some rotation, then every energy function has to be taken into account in this U. And then we have to take the derivative of this U to evaluate the forces in each atom. And how to update the position of the or velocity of the atom. So initially we have this initial position and velocity. So we have to update this over in the incremental time. So for one time step, how much it will move with how much velocity. So that is done with the help of Taylor series expansion. So for example, we have to identify what is the position at next time step. So this will be expanded in the Taylor series. So this is a Taylor series extension. Similarly, we can use this expression for the previous time step. So it will give this expression. And the higher these terms can be neglected because delta T is already very small. It is of the order of femtoseconds, picoseconds or femtoseconds. So it is already very small. So higher order terms can be neglected. And if we add this, then we can get this next time step position, which is nothing but this expression. So it contains this force and this current position, the previous position, and this delta T we know, M is already known, and this force comes from the negative derivative of the potential energy. So in this way, the next position can be updated every time. And similarly, we can update the velocity. We can just subtract these two, then we will get the velocities as well. So in this way, by this algorithm, which is known as Verlet algorithm, we can update our positions and velocities of the atoms in the system. And since these empty simulation settings, so we start with our atomic position. As I said, that initial position should be known. After that, we have to apply whatever the material properties there in this material, like density, mass, charge, lattice constant. So these kind of things we have to mention in the code. Then we have to supply this with initial velocity. So initial velocities basically depend on the temperature. So that depends on the lattice Boltzmann constant, or this equation that half mv square is equal to 3/2 k into T. So from the temperature, we can obtain the velocities. And then we have to apply the periodic boundary condition, because we have to simulate the bulk material properties. So usually we take it in nanometric scale. So if we have to simulate the bulk material properties, we have to consider this periodic boundary condition. I will explain it later, but it's this PVC. And then after we take the atom position and velocities into account, we have to set the interatomic potential energy function between that, because otherwise there will be no repulsion or attraction between those atoms. So for that, we have to supply it with some potential energy function. So there are different potential functions which are available in the literature. And after that, we have to select appropriate time step, and it should be usually of the order of femtosecond, because if it is larger, then we cannot understand the phenomenon which is happening at very lower time scale. So for understanding all the phenomena, we should select the least time step, and then we have to we have to apply the constant, like what is the condition, like if temperature is constant or if energy is conserved, or if pressure or temperature is constant. So those conditions should be enforced into the simulation set. Now PVC, as I said, that this is usually, so likewise, this is our simulation set if we consider it. So usually this is of nanometric scale. Now, if we consider the nanometric scale size, so there would be very high amount of boundary effects, because surface area compared to volume is very large. So to eliminate those surface effects, we have to consider, we should virtually consider the images, so that we will do the simulation in this box, but virtually it will be having infinite images. So this will eliminate our boundary or surface effects. So these are virtual images of this simulation box in all sides in 3-dimensional space. So if any atom moves out of this boundary, so because our condition is that number of atoms should remain constant, so the atom from the other box, it will enter from the other box to this main box. So this is our basic MD algorithm, that first we have to supply the initial condition for position and velocities. Then we get the forces by equating it with the potential energy function. And then we update the position and velocities over time with by giving the short time step. And then we run the simulation for maximum time, whatever time is specified. And if that is not completed, these steps will keep on repeating in the loop. And if it reaches the maximum time, then your simulation will be over that by that time. So this is our basic approach for MD simulation. Now I come to nanoscale machining process. So which is a single point diamond turning process, which I have carried out during my PhD research work. So it is basically an ultra precision machining process. So it's a nano region machining process in which the surface finish can be obtained within few nanometers. The shape accuracy can be achieved within tens of nanometers. The size tolerances can be achieved in hundreds of nanometers. So everything is in nanometer. So we cannot achieve these in nanometers if our cutting dimensions are of millimeter size. We have to use those cutting dimension in nanometer size, then only we can achieve the surface finish in few nanometers. So start with what is the significance of this ultra precision machining. So in the year 1980, the Taniguchi predicted for these different machining processes that how they will behave in during after 2000. Is like in 2020, what will be the nature of these processes? So he found that the ultra precision machining process, which is single point diamond turning, it will reach the machining accuracy of 0.01 micron, which is nothing but 10 nanometer. So this shows that the ultra machining process is able to produce better than 10 nanometer accuracy. And to get that nanometric level accuracy, the processing scale should be extremely small. Then only we can achieve this nanometric accuracy. And single point diamond turning is the approach which can help in achieving this nanometric accuracy with very low cycle time. So now I come to the diamond turn machining or single point diamond turning. It is basically a deterministic nano region machining. Deterministic means tool path can be controlled. And as I said, that the size tolerances, shape errors, and surface finish can be achieved within the order of nanometers. So basically, it is like a normal lathe machine, but this is supplied with very high-end technologies. Like for the spindle, here the air bearing spindle is used, and for the slides, the hydrostatic slides are used. So that can control the motion within the accuracy of nanometers. So then only we can achieve our these cutting dimensions in the order of nanometers. So basically, this spindle rotates this workpiece clockwise or anti-clockwise, and with the help of this relative movement with the tool and workpiece, we can achieve the material removal. Now, this tool, if we take this line, so we can see in the cross section, this can make this kind of feed marks on the workpiece, and this is known as critical chip thickness. If below this chip thickness, no material removal will take place. So this is called the critical chip thickness. If it is more than critical chip thickness, then only the material can be removed. And if we analyze closely this tool and workpiece interaction, so we can see that the tool radius is in the on nanometer, and the cutting depth is also of the order of nanometer. So when these two are these cutting dimensions are in the order of nanometer, this radius and the uncut chip thickness, then it means the atomic clusters of the tool and atomic clusters of the workpiece are interacting with each other, because only there is a nanometric size of the tool, and then the cutting uncut chip thickness is of the order of nanometers. Then that means they are interacting at nanoscale. So coming to diamond turn, this machine, so it has evolved over the years. So it started from the 1960, where the air bearing spindle were developed, and after that some feedback devices like optical encoder, which has the accuracy better than 100 nanometer, those were developed. And after the development, in the year 1999, the first diamond turning machine was developed, and after that regular developments took place. So, and in the year 2010, this high-end machining, which has the capacity to generate free-form structures, micro features, and size, shape, and surface finish of the order of nanometers could be achieved. So it took a long journey and a long time to achieve these kind of high-end surfaces in the by the diamond turning process. So if I differentiate between the conventional cutting and nanoscale cutting, so in the macro scale cutting, usually your chip thickness is around hundreds of micron or sometimes in millimeter. So in that case, your tool, this uncut chip thickness is very large than the tool edge. But in the case of nanometric cutting, it is less than 100 nanometer, hundreds of nanometer. So there, your tool edge becomes dominant, and your with respect to uncut chip thickness, this edge is very dominant. So in this case, the compressive forces or compressive stress is very high as compared to this macro scale cutting. So this is the basic difference, and mechanisms also get changed. Here you can see the shear plane cutting mechanism. The chip comes over this rake face of the tool, but in this case, because there are compressed stresses, so material can have the extrusion kind of mechanism. Extrusion means it can go either side of the tool. And mechanics in this approach, because it is a macro scale cutting, we go for continuum or homogeneous approach because it's a larger scale. So we can consider the material as homogeneous in nature. Whereas in this case, since nanometric size of tool and nanometric uncut chip thickness are being interacting with each other, so we have to go for atomic scale simulation because it is showing the heterogeneity, that atoms in the atom clusters of atoms are interacting with the tool in the tool and workpiece. So simulation method, as I said, that it is a continuum scale approach. So we can go for finite element method for the macro scale cutting, but molecular dynamics simulation can be adopted for this nanoscale cutting. And since there is the chip load is more on the rake face of the tool, so most amount of wear that takes place is on the rake face, and it comes in the form of abrasion, adhesion, or thermal. But in this case, the most of the material is in touch at the flank side of the tool surface. So mostly the wear takes place on the flank face of the tool. And most dominant wear mechanisms are abrasion or chemical. And the specific cutting energy, which is the cutting energy required to remove a unit volume of material. So it is very low in this case. The energy requirements are very low, but it is significantly higher in this case. So for this research, the motivation comes from the thing that the conventional machining has very high surface roughness on the materials surfaces, but in the diamond turning, you can achieve very low level, this low amount of surface roughness. It's of nanometric level. And if we see the tactile machining, so metals can be smoothly machined, but in case of brittle materials, we get that fractured surface. And the motivation comes that if we have a heterogeneous surface, like alloyed surface, where there are hard inclusion or particles, the mechanisms were not well understood. So in my PhD, I took that heterogeneous material so that it can be studied with the help of molecular dynamic simulation, that how does it behave during machining, nanoscale machining. So for that, I carried out the decade-wise this literature survey on the SPDT process, the single point diamond turning process. So I found out that in the decade-wise, it has this machining technology has been developed. Initially, the machine tool building took place in the first decade, and after that, slowly they carried out some machining and they understood some process mechanics on some soft materials. After that, they went for understanding of material removal mechanisms, surface quality, the tool performance, or crystal orientation. In the decade from 2005 to 15, they try to understand the brittle materials machining, tool wear. The molecular dynamic simulation was also introduced in this decade. And after that, they tried to study the wear mechanism as well as the micro feature generation and freeform machining. And in the current decade, there was a challenge to study these difficult to cut materials or heterogeneous materials, or we can say hybrid materials. So that's why I selected that copper beryllium material to study, because it contains some hard particles. It has the soft copper matrix and has the hard particles in between. So that is difficult to machine. So that I have studied with the help of molecular dynamic simulation. So in the as I said that there was research gaps like hybrid material machining with diamond tool had received a little attention, and then this effect of work material, mechanism of material removal, tool edge condition, machine tool vibration on the diamond surface were not extensively studied. And then material removal mechanisms for at nanoscale is also not clearly understood for different materials. And then tool wear, it's a critical issue because the diamond tool is very expensive. So tool wear needs to be understood for machining any material. Otherwise, if tool wear is more, then it can lead to a very large cost of the machining. So it led to some objectives like the tool and hard particle interaction during machining of hybrid materials. Then objective like molecular dynamic simulation has to be applied to understand the material removal mechanism as well as tool wear mechanism and the effect of on the diamond turn surface or subsurface damage, and also the tool wear model which needs to be developed based on the mechanism and tool condition monitoring. So coming to numerical simulation of machining. So here, if the uncut shiftingness is of the order of millimeter, so we need to go for finite element scale. And if it is less, then we can go for mesoscale. If it is more or less, then we have to go for this molecular dynamic simulation approach, where it is the uncut chip thickness is of the order of nanometers. So coming to molecular dynamic simulation of nanoscale machining process. So basically what we do here, that tool is given the velocity, which means the tool atoms, their position and velocities updated. So this applies the force on the workpiece atoms. So this also changes its position and velocities. So that has to be updated every time. So with respect to time, these two means atomic atoms of the workpiece, and tools have to be updated and see what changes are occurring on the surface of the workpiece. So for that, I modeled my tool and workpiece. So I initially took the copper as my workpiece. So workpiece was converted into atoms. So there are atoms in the workpiece. So it has the length of 30 nanometer, the height of 12 nanometer, and width is of around 18 nanometer. And we have to mention the cutting plane and orientation because it is at the nanoscale. So this comes in actually crystal structure. So we have to mention the cutting plane and direction. So in this case, I took the 010 plane and this 100 direction for the cutting. And copper is considered, so it has the FCC structure. So it was mentioned in the code that the copper atoms should be created with the FCC structure. And tool is a deformable, which is made up of single crystal diamond tool. That's why it is known as diamond turning as well. It has the diamond cubic structure. And these are the number of atoms considered in the tool and workpiece. The cutting edge radius is around 2 nanometer. The chip thickness is varied from 2 nanometer to this 0 angstrom. Cutting velocity is around 1 angstrom per picosecond. The equilibrium temperature is around 293 Kelvin. That means that this cutting has taken place in at 20 degrees Celsius temperature. And time step is 1 femtosecond, that is 0.001 picosecond. Now, if we see this model, so this has 3 layers. So first one is the boundary layer, which is the extreme layer. So this is the rigid layer which supports these Newtonian layer atoms and thermostat layer atoms, which is the second. So if we don't provide this boundary layer, so when our tool will move, so it will force this workpiece to move. So it will also this workpiece will also move if we don't apply this, have this boundary layer. So boundary layer has fixed atoms. So they keep this workpiece at the same position. Otherwise, it will also move due to the tool velocity. The second one is thermostat layer. So it keeps the constant temperature in the workpiece because it is a very small workpiece of the order of nanometers. So any cutting happens, so it can generate a large amount of heat, which is very difficult to dissipate it. So in the real scenario, it can be dissipated because there the workpiece atom is very large. But here the workpiece is very small, so it will not be able to dissipate that much heat. So that's why thermostat layer is provided, so that can dissipate extra amount of heat. And the third one is Newtonian layer. So this is a layer of atoms in which the actual dynamics takes place. So these 3 layers are provided in both the tool and the workpiece. So this is the 2D view of tool and workpiece. So since as I said that initially these atoms are defined, their positions are defined. Now we have to supply the interatomic potential energy function. So for the copper and copper interaction in this workpiece, the copper and copper interaction will take place the EM method, that is embedded atom method. For the metallic system, we use the embedded atom method, which is popularly known and it is available in the literature as well. For the tool, since it is made up of diamond, that means it has the carbon-carbon bonding, which has the covalent bonding. So that is basically can be easily their interaction can be easily analyzed with the help of Tarskov potential. So there we need to model it with the Tarskov potential. And between the copper and carbon, because here it is carbon, in the workpiece there is a copper atoms. So in between the copper and carbon interaction, the Morse potential is used. That is very good potential to study the surface interaction between the tool and workpiece. And here A is the uncut chip thickness and R is the tool edge radius, the cutting edge radius. And software which I used for simulation was LAMPS, and for visualization there was Ovito software. These are the this formulation of these different potential function, the E for the EM potential function and for the Tarskov and for the Morse. So since if we run the simulation, first thing we have to validate those simulation results. So we cannot compare one-to-one comparison because this is taking place at nanoscale and in our experiments, your tool and workpiece are usually large. Only the cutting zone is small, but these tool and workpiece are very large. So we have to find a way to validate these results. So what I did, I took one sharp tool and one round edge tool and evaluate their forces when the cutting took place. So for the this sharp edge, so there is MD simulation and there is the experimental results. So for the MD simulation, we can see for the sharp edge, the cutting forces are high and thrust forces are low because the chip load will be more on the rake face. So here the cutting forces will be large. But in the case of this round edge, your this chip load will be distributed. It will be equal in both the rake face and the flank face. So your thrust and cutting forces will be almost equal. Similarly, I carried out it for the sharp cutting edge and round cutting edge for in the experiments. So it also showed the similar phenomena. So for the sharp edge, the cutting forces were more than thrust forces, and for the this blunt cutting edge, it was almost similar. And if I compared the force ratios, that were close in both the sharp cutting edge and the blunt cut or the round cutting edge. So after this, after validation, I studied this material removal mechanisms for nanoscale cutting of copper for different these parameters for different A/R ratios. So that varies from 2 to 0. And it showed that the material removal took place by the dislocation flow. So these are the dislocations which are flowing, and these propagate in 110 directions. So in every A/R ratio, basically the radius is same. We are changing the uncut chip thickness, so it is being reduced. So initially there will be shear plane deformation, and after that there's extrusion mechanism that takes place. So some of the material goes beneath the cutting tool, and once it is very much reduced, the uncut thickness, then only elastic deformation that is taking place. Now no cutting is taking place, so only rubbing phenomena is happening. So based on these force ratios, we can define those 3 cutting regions in the this cutting simulation. So for A/R greater than 1, there is shear plane deformation. That means through the shear action, this cutting is happening or chip formation is taking place. For A/R ratios from 0.25 to 1, the plowing mechanism is taking place. So plowing means the material is going sidewise, or means this extrusion-like phenomena is taking place. The half of the material is going ahead of the rake face of the tool, and similarly some amount of the material is going beneath the tool. And for A/R less than 0.25, there is only elastic deformation is taking place. Similarly, I carried out the cutting simulation for different crystal orientation for the copper workpiece. So 6 different orientations were considered for this simulation, and different uncut chip thicknesses were taken. Other parameters were same, but these 2 things were changed. So if we take this orientation, that means the 010 plane and 100 direction. So similarly, we can change the orientation of the this cutting plane and direction. So what I see that these slip-induced deformation dislocation that took place, and that mostly took place in 110 direction, and because 111 plane and 110 direction is usually this, it denotes the slip system, means the shear slip can be formed easier formed means easily in this cutting orientation. So that's why in the 110 direction, these are most dominant. So we can see that most subsurface damage, it took place in this orientation, where the 110 direction is in vertical direction. So since 110 is oriented in vertical direction, so there it has slip can propagate easily in this direction, and thus substantial surface damage can occur. Similarly, if we check the variation of forces and cutting energy, so we can see that the maximum force took place for this orientation, 011 and 100 orientation. and minimum for 111 and 110 because it denotes the slip system. So it is very easy to deform in this orientation. So there the minimum amount of force is required to deform the material. And also this specific cutting energy graph shows that in the lesser AYR ratios increase your specific cutting energy, which means if the energy is more, the tool wear can be more in these lesser AYR ratios. And also it shows that it is found to be minimum for this, as I said, 111, 110 plane orientation and maximum for 011 and 100, similar to the cutting forces. So by the help of these graphs, we can show that in the copper material, it is very difficult to machine this orientation 110 and 001, but it is easier for this orientation, the 111 and 110. So similarly, I studied for the copper beryllium. So for copper beryllium, usually in copper beryllium acts as very hard particle inside the copper matrix. So this material is extensively used in nuclear industries as high-speed bearings, but it has the limitation that it can cause excessive tool wear and surface degradation. Because during the machining, these hard particles, when encountered with the workpiece, they cause the tool wear. So the objectives here were to study the material removal mechanisms using molecular dynamic simulation and to identify and understand the wear mechanism of single crystal diamond tool during the machining process using MDS and experimental investigation. And similarly, on the surface, what effects come. So that effects has to be studied with the MDS and experiments. So similarly for copper beryllium, the model was prepared. So for workpiece, which is made up of copper that has HCC structure, in this workpiece, the beryllium particle was introduced, which has the HCP structure, hexagonal closed packed structure. And for the tool, this covalent bonding is there. So this diamond cubic structure is there. And the interactions are for copper and copper. The similarly AEM potential was used for carbon and beryllium and carbon. Since covalent bonding is there, the Tresov potential was used. And for surface interaction, the Morse potential was used. And similarly here, the Wandry layers is used in both the tool and workpiece to support these Newtonian layers, and thermostat layer is used to dissipate the extra amount of heat. And some assumptions were considered, like beryllium rich phase consists of this pure beryllium, and where the base material is made of pure copper, and these are considered to be in spherical in shape. In reality, they can have different shape, but here it is assumed for simplicity that the spherical shape was considered. And simulation was considered carried out at 293 Kelvin, and system follows NVE dynamics. Here the thing was that the copper beryllium parameters were not available in the literature, this interaction potential energy function. So for that, I applied the first principal calculation, which is the quantum simulation based approach to evaluate the parameters for interatomic potential. So for that, what I did that I took two atoms, copper and beryllium. So their differences, their distances were changed. So based on this quantum mechanical effect, so initially, when the two atoms were at far away distance, there was some weak attraction. So at when they were brought to with closer, so attraction becomes stronger. And once they are brought more closer after this equilibrium distance, so there was some repulsion that was shown. So with higher energy means least stability and lower energy means more stable. So here the structure is more stable. So at this point, these parameters were extracted and these were fitted with the Morse fitting parameters. So Morse function is this one. So here the parameters were evaluated like D is the binding energy, which is nothing but this parameter minus 0.0563. Similarly, there is alpha is width parameter. So how much width it assumed, and the equilibrium distance, which is at 2.065. So these parameters were evaluated, and this function was incorporated in molecular dynamic simulation. And after that, these latest constants were evaluated. So usually what happens that for creating the structure in the simulation, I took the lattice constant from literature. So for copper, carbon, and beryllium. But in the literature, these constants are given at different temperatures. So, but I am carrying out my simulation at 298 or 293 Kelvin. So I have to first find out these lattice constant at this temperature, because I am carrying out the simulation at this much temperature. So these lattice constants are not valid at that temperature. So for that, the NPT dynamics were played, and it was seen that there was initial fluctuation, and after that, they were just fluctuating around some constant values, all the latest parameters for copper, beryllium, and carbon. So in this region, they were averaged out, and it was found out that there was some differences between the lattice constant from the literature. So these lattice constants were considered for creating the structure in the MD simulation code. And once the structure was defined in the MD code, so MD simulations were run, those simulations were carried out, and results are being presented here. So what happens initially when the tool cuts in the workpiece? So there are shear plane deformation that took place in the copper region. But as soon as it encounters the particle, so because particles being hard in nature, it is pressed against the workpiece. And when the tool moves over the particle, because of the elastic recovery, it comes out of the workpiece. So the workpiece has certain voids and projection. And also when the particle was closely monitored using MDS, so it was seen that since it is hard and brittle in nature, so there was some crack formation that took place in the particle. So this amorphous cracks were generated. This is shown by the amorphous layer. So these are beryllium atoms, the black one, and this shows the cracks which are separated by this white color amorphous layer atom. So which shows that there is brittle transition which is taking place in the particle, brittle material, brittle fracture. And it was also observed in the experiments that when the surface was analyzed on these beryllium particles, so there were cracks. These cracks were observed in the hard particles. So similarly, these dislocations were also analyzed. So it was seen that initially this copper has this certain dislocation, and when it comes closer to hard particle, so they become nucleated because this dislocation flow is hindered by the hard particle. But after this tool faces this hard particle, so it starts pushing this hard particle. So this hard particle itself forces the copper material ahead of this particle. So a lot of dislocation that are generated because of the force that is coming from the hard particle, which is in turn coming from the cutting tool. So a lot of subsurface damage which was occurring due to this hard particle. So if we can see this dislocation length graph, so we can see for the copper and copper beryllium in the particle region, there is a lot of dislocation that is taking place. So that means in this particle region, there are a lot of large amount of subsurface damage that is taking place due to this formation of long dislocation loops. And here the specific cutting energy was plotted, and it was seen that almost all the graphs were overlapping. And so it can be concluded in copper beryllium material that grain orientation effect is overcome by the presence of hard particle. So similarly, some experiments were carried out for tool wear. These are the parameters which were used for understanding the tool wear. And after that, it was also the mechanisms were also understood with the help of MD simulation. So this is the experimental setup, which is the diamond turning facility. So here it is a spindle, there's a tool post. So in the spindle, there's a vacuum chuck because we cannot handle these fragile components in mechanical chucks. So vacuum chuck was used, and the hydrostatic slides were used for the movement, and air bearing spindle was used in the simulation, in the experiments. So when I plotted the wear length with respect to cutting distance, it showed the extent of tool wear. So in copper, it almost covered more than 20 kilometer of this the cutting distance. But in case of copper beryllium, this the flank wear was very dominant. So it can be identified by 3 regions in the copper, but in the copper beryllium there were only 2 regions, because after the initial wear there was a catastrophic amount of wear that took place in the copper beryllium in the tool that was used on the copper beryllium. And it was found that the tool used on copper beryllium has 60% lower life than that was used in the copper. So I tried to find out this difference between the copper beryllium and copper for the tool using MDS. So here I took the sharp edge tool and the blunt edge tool, and this workpiece material was considered with the this beryllium particle, and it was seen that when the tool encounters this hard particle, so these stresses were quite high at the edges. So the structural analysis showed that the microchipping was taking place in the sharp edge tool when it encounters the hard particle, and in the round cutting edge there were amorphous layer that was generating. That means the phase transformation that was taking place in the case of round cutting edge. So it can be concluded that the sharp cutting edge, due to sudden impact load, it causes a very high stress at the sharp cutting edges, which causes the microchipping. And in the blunt cutting edge, the stress induced phase transformation that weakens the cutting edge. So it was also seen with the help of coordination number. So here the coordination number means in the bulk it is varies between means in the bulk it is 4, and at the outside, because on the surface atoms it showed 2 and 3. But here we can see that there is amorphous layer that is being generated. So basically amorphous layer weakens the cutting edge and it dominates the tool wear mechanisms. And it was also seen with the help of experiments. So when I carried out the Raman spectroscopy in the tool used for copper as well as copper beryllium, so it was seen that for copper there was only a single peak. So that showed that only sp3 diamond was there on the tool. But in the case of copper beryllium, the tool showed that there was one single larger peak that corresponds to diamond, but there was another peak. So that is corresponds to D band, or that corresponds to amorphization of the diamond. So some amorphous layer was formed, which was shown with the help of experiments as well. So we can state that for copper there is atom by atom removal of tool atoms, and for copper beryllium the tool wear takes place by phase transformation. So similarly, it was seen that on when the thermal spectroscopy was carried out on the copper beryllium surface. So basically what happens that when the tool wear takes place, the atoms from the tool, they come on the workpiece surface. So surface was also analyzed with the Raman spectroscopy, and it was seen that at different cutting distances, there were different peaks that was observed. So it means that amorphization, the amorphous atoms were increasing, which is shown by this peak at 1400 centimeter inverse. So this keeps on increasing, which means the amorphous atoms are getting more and more on the workpiece surface. Whereas in the case of copper surface, there was single larger peak which correspond to diamond only. So there was amorphization which was taking place in case of copper beryllium, but in case of copper, there was only the atom by atom wear of diamond that was taking place. So coming to surface roughness, so similar cutting parameters were used, and surface was analyzed for roughness. For the F15 analysis was carried out. The morphology was seen on the surface, and some contamination, if that took place on the surface, that was also analyzed. So first thing, as the tool wear graph, similarly surface roughness was analyzed. So it was seen that similar to tool wear, the surface roughness also increased on both the copper and copper beryllium, but the extent of surface roughness was more in copper beryllium. So it was there was almost a 48% increase in surface roughness as compared to copper. So by checking on the SCM images, so it was seen that for copper there was well-defined this pattern is there. So it was seen that deterministic lay pattern was obtained for copper. But in the case of copper beryllium, so there was no pattern that was seen, no visible pattern like copper, although the similar parameters were used, but only the flat this surface was analyzed. So it was initially expected that random lay pattern has been introduced on the copper beryllium surface. So it is expected that maybe hard particles have caused this transition of lay pattern. So then I carried out FFT, that means fast Fourier transform, which means that if we have 1 mm of surface profile, and if there is a this feed marks are of 2 micron, then the peak will be observed in 500 Hertz frequency region. So for the copper surface, these 500 these frequency marks were obtained, but in case of copper beryllium, there was no 500 frequency marks. So that means those feed marks were not there, and there were dominant frequencies that were obtained. It was basically in between 0 to 30 per mm that those components were there. So these are very low frequency components. So what could be the reason for that? Again, I carried out the MD simulation. I introduced the feed marks on the workpiece itself and considered the hard particle in the simulation. So what I saw that when the tool interacts with the particle, so the tool has movement in the horizontal direction due to the force caused by the hard particle. So that levels this feed marks. And it was also analyzed with the help of this force diagram, which showed that in the beryllium particle region, the lateral force become very much high. So that was seen with the molecular dynamics simulation. The lateral force become very high. So that caused the movement of the tool in the lateral direction, which levels these feed marks. And it was seen that lateral force is was 5 to 6 times higher than when it cuts in the copper. So lateral forces were the region that was responsible for leveling these feed marks. And also I checked in the experiments. So that also showed that initially the cutting forces were higher, but as the tool wear took place for copper beryllium, so the lateral feed forces were high. So in case of copper, the cutting forces were higher, and for copper beryllium, the lateral feed forces were higher, which were causing the tool to level that surface. So that's why the random lay pattern was observed. So after that, I analyzed the surface for any chemical contamination. So basically, the X-ray photospectroscopy on copper beryllium surface was carried out, and it was seen that for copper and copper beryllium, following peaks were seen that at 284.8, which correspond to carbon-carbon peak. 286 it is carbon oxygen peak, and 288 that is C double bond O. So these 3 peaks were observed. So basically in copper, mostly the CO and C double bond O peaks were dominant, but in copper beryllium, the carbon peak is dominant. So it showed that by also comparing it with Gibbs free energy, we can see that which reaction is dominant. So if we check all these chemical reaction, so delta G is more negative in these 2 cases. So that's why these 2 reactions are more dominant on the surface, whereas it is higher energy. So these are not feasible reactions. So basically the oxidation of diamond tool on the workpiece that is taking place. So delta G is lowest for carbon dioxide and carbon CO. So that's why the oxidation of these worn out diamond atoms that is taking place on the workpiece. And in copper beryllium, the surface contamination is mostly taken place by the carbon-carbon bonds. That is just the wear particles from the tool. And also this physical and chemical interaction between the tool and workpieces also affected this chemical, mechanical, and optical behavior. So XPS, that X-ray photospectroscopy, showed that if we etch for some time, so it showed that the percentage of carbon beneath the surface. So it was more on the surface initially, and as we etch it for larger time, so it showed that at the about 5 to 6 nanometer, there was some contamination of carbon atoms. So that means the carbon atoms from the diamond has diffused on the workpiece surface. Similarly, the nanodatation was carried out to evaluate the hardness and elastic modulus. So it showed that it was carried out different depths from the top of the surface. So it showed that for top of the surface layer, there is a hardened layer that was observed. But in the bulk layer, this hardness is same. But on the top layer, which is around 60 to 70 nanometer, there is hardening that is taking place. So that is residual stresses that has occurred on the surface due to the compressive stresses from the tool. And similarly, similar thing was shown in the elastic modulus graph. So coming to optical reflectivity, since these surfaces are optical surfaces, because these are nanometric surfaces, so optical reflectivity was also checked for copper and copper beryllium, and it was seen that these surfaces for copper, it showed that these are applicable for infrared region as well as visible region. So this visible region is 400 to 700 nanometer, and after that it is 700 nanometer that belongs to infrared region. So copper surfaces are more applicable for the infrared as well as visible regions, whereas in this copper beryllium, so since it has more these dislodgements or voids and projections, so it is mostly applicable in infrared region. So in the visible region, its optical reflectivity falls very rapidly. So this is mostly applicable in infrared region. So coming to this major conclusion. So basically, I tried to find out the wear mechanism and surface generation mechanism, and it was found out that the dominant mechanism was the phase transformation in the form of amorphization that was identified as a new wear mechanism in the diamond tool when it was used on copper beryllium. And in the surface, workpiece surface, the random lay pattern was obtained, which was due to the beryllium particles that caused the suppression of deterministic lay pattern. And the material removal mechanism in case of copper beryllium is phase dependent, which means that in case of copper phase, the tactile machining mode was observed, whereas in case of hard beryllium phase, there was brittle fracture that took place. The other mechanisms are, as I said, that the material removal mechanism is phase dependent. So in copper, if we take there was shearing action, the plowing action, and then elastic plastic deformation based depending on the A/R ratio. And in the hard beryllium phase, there was brittle fracture. And if we lower the A/R ratio, we can have the ductile region cutting condition as well. And tool wear in the copper beryllium. So in the initial phases, there was microchipping, so abration was taking place. But in the later stages, there was phase transformation, which was dominant. And since as I said, that a random lay pattern was observed in the copper beryllium surface, whereas deterministic lay pattern that was observed on the copper surface. And smooth surfaces in the case of copper beryllium, copper surface, copper workpiece, whereas there was dislodgement of hard particles or fracture surface at the hard particle location, which was observed in the copper beryllium. If we compare the tool life, so cutting distances covered on copper is 18 kilometer, whereas it is 8 kilometer in case of copper beryllium. So copper beryllium causes more tool wear. The wear mechanism is atom by atom, that is called the attrition wear in the copper material, whereas in the case of copper beryllium, there is the phase transformation of the diamond. to amorphous layer. And if we compare the surface roughnesses, there was huge difference between the surface roughness. The maximum difference of 52% was observed in between copper beryllium to copper. And also there, the surface contamination that also took place in the form of oxides of the carbon and copper. And in the copper beryllium, there was diamond particles was observed on the surface. So that was all from my side. So thank you all for patiently listening to this presentation. If there is any query, I am open to any query if you have.
Participant session is open for question and answer. If you have any question, please ask the question. Dr. Anuj, just a small basic question from my side.
Yeah.
For simulation, what types of softwares are useful?
So for molecular dynamic simulation, there is a well-known software that is LAMPS. So that is used for writing a script file. So that script file is run on that LAMP software, and that output is visualized in the Ovito software, or that is open visualization tool. And these are open source code, so these are readily available in the online. So these are not commercial software; these are online available. So anybody can try their hand on this LAMP software and Ovito.
Sir, for heat source fitting, is it some kind of some models is specifically you can use
Sorry, could you repeat the question?
for cutting and finishing some specific heat, or we should remove some particular point of source modeling we use?
No, in atomic scale simulation, you have to supply this interatomic potential energy function, because this is a very fundamental simulation. So it will automatically generate that heat based on the velocity of the atoms. So basically what we are applying that the formulation is based on the Boltzmann constant. So basically any atom has the kinetic energy. So that is equated with that Boltzmann equation. So for example, any atom has a kinetic energy half mv square. So that is equal to 3/2, the Boltzmann constant, into temperature. So temperature can be evaluated with respect to velocities of the atom. And velocities we can find out from the algorithm of MD simulation.
Participant, if you have any question, please ask. Sir, some participant asking about your presentation. Is it okay to share your presentation?
Yeah, I will share with you. You can will share with them. Yeah, no problem.
Participant, you can just unmute and you can ask a question. If you're having any doubt, you can just unmute and you can ask the question.
So if anybody has question, if they can ask later as well, you can have my email ID and you can email me as well. There's no problem.
Okay,
And-
sir, email ID and contact number I will collect. If anyone wants to, in future, if you want to ask some question, you can contact sir.
Yeah.
On the behalf of Aditya University, I really thankful to Dr. Ramesh Sharma for sharing their valuable presentation and their expertise in this particular area. Thank you, sir. Thank you so much. Now
Thank you,
I'm
sir.
inviting.
Thank you very much.
Yeah, thank you, sir. I would like to thank Dr. Jubair and his team for inviting me and sharing my presentation with all the participants. So thank you very much.
Thank you, sir.
Okay, thank you, sir. Thank you so much.
Now
So
I'm
shall I?
introduce.
Can I leave now?
Yes, sir. You can leave it, sir. Thank
Okay,
you so
okay.
much.
Thank you. Thank you so much.
Now I'm inviting our next speaker, Dr. Mohammad Zahir Khan Yusufzai. It's an immense honor to introduce our distinguished speaker, Dr. Mohammad Zahir Khan, sir, a highly accomplished professor in the Department of Mechanical Engineering at IIT BHU, Varanasi. Sir holds a PhD degree from IIT Delhi and made a significant contribution to the field of welding, material engineering, grinding, and metal characterizations. With extensive research experience, Sir has deep expertise in friction stir welding and innovation in manufacturing process. His remarkable work has earned from him numerous awards and honors, including the Fieldman Award 2019 for the best paper on automation and process development by the Indian Institute of Welding, as well as multiple best papers and best project awards at national and international conferences. A dedicated researcher and a mentor, Sir has completed successfully guided 39 MTech students and 9 PhD scholars with several ongoing projects under his supervision. His research initiatives, including the SERB DST project and SARAS sponsored projects, focused on the metal characterization and residual stress assessment in the welding and advanced coating for the high temperature materials. Dr. Khan is an active life member of prestigious professional bodies such as the Institute of Engineers, Indian Institute of Welding, Indian Society for Non-Destructive Testing. His profile contribution includes numerous publications in reputed international journals, international conferences, national conferences, shaping an advancement in welding technology and material science. Beyond the research, Sir has played a vital role in the administrative and academic leadership by serving key positions at IIT BHU, including the chairman of the Design and Innovation Hub, member of the main workshop committee, and several works. We're privileged to have Dr. Khan sir with us today and to share his knowledge and expertise. So please join in extending a warm welcome to our esteemed speaker. Sir, am I audible to you?
Yes, yes, you are very much audible. Am I audible?
Yes, sir, you are audible, sir. Now, sir, you can share your screen.
Sure, sure. So my camera is also visible. You can see me.
Yeah, camera is visible. If you want, you can switch off camera also. You can share your
No,
screen, sir, as
it's
per your
okay.
wish, sir.
Yeah, it's okay.
It's better to make your camera on, please.
Okay, so I have shared my screen. Is it visible?
Yes, sir, it's visible.
Okay. Is it on the slideshow mode?
Sir, now it's clear, sir.
It is on the slideshow mode, right? And the slides are also moving?
Yes, sir, it's more.
Good. Okay, so a very good evening to all of you. Thank you, Zubair, for the invitation, for hosting me, letting me meet a wonderful gathering of people, although virtually. Thank you for the generous introduction also. So, as Zubair has informed, basically I'm a teacher, I'm a professor in the Department of Mechanical Engineering at IIT BHU. On the background, you can see the nice photograph of the beautiful IIT BHU campus. And somewhere in this huge building, we have Department of Mechanical Engineering also, although it's not very much visible on the facade. I will be talking about on one of the important topic, that is on the analysis of the friction stir cladding process, which is a new process in the sense that an innovation has been made to the existing process. But before I start, a little bit about what we are currently doing in IIT BHU. We have actually, as Zubair told, we have supervised almost 45 master's students and 10 PhD students. Some 6-7 students are already currently working on their PhD work, and 6 MTech students are also working in the area of welding or its allied processes like additive manufacturing, joining and cladding. We have developed some facilities also, mostly related to welding and additive manufacturing at IIT Beach, the Department of Mechanical Engineering. That includes the conventional arc welding processes like GTAW process, pulse GTAW process, GTAW process, projection welding, plasma arc welding. We have submerged arc welding, CMT with robotic arm is present, ultrasonic welding machine is there. We have got friction stir welding machine also, and this we are having since the year 2014. We have got weld mechanization facilities, so whatever welding is carried out, either it is carried out by the robotic arm, or we have got for linear welding, we have got weld mechanization that has been somewhat indigenously developed by us. Some of the components have been purchased from other vendors also. We have got weld testing facilities like the conventional facilities for taking out the optical microscope, microstructure, micro hardness testing, tensile testing, Barkhausen noise analysis technique, which is a wonderful non-destructive technique of estimation of the material properties. And these weld testing facilities or material testing facilities we are having with our research group. Apart from that, the department also have a lot of other testing facilities. We have got central instrumentation facilities where all XRD, SEM, TAM, all sort of setup are there. The central instrumentation facility, which we also use and our student also use. Recently, we have also added to that laser welding and laser cladding facility. We've got a 3 kilowatt laser welding and laser cladding facilities with our group, which we are using. On the right hand side, again, you can see a beautiful picture. There is a temple inside our campus, BHU campus, in fact. And this is an aerial view of that beautiful temple. Okay. So before I start with my lecture on cladding, I'll just warm up by discussing what is welding. We all know that welding is basically a method of permanent joining of the material, whether you are joining end to end, you are one material on top of the other, or you are joining or adding several layers of material one after the other, just like what you do in the case of additive manufacturing. So all this requires that there should be a permanent joining of the material that has to take place. And this permanent joining, why I'm calling it permanent joining, is that after a layer of material has been placed on top of another material, it is really undifficult. It is really difficult to unjoin the process. And you have to, if you have joined something by welding and good quality welding, it is impossible to separate them or unjoin them. The only method by which you can separate those pieces or you can separate different layers is by again performing machining. Just as you have to do machining if there is one single piece of material, not many different pieces of material. And this is possible, this permanent joining possible because in the case of welding, the bonding takes place at the atomistic level. There are some constraints that are there wherever we are building materials through welding, or we are depositing a layer on top of another material by welding, or we are joining two pieces of metal together. And those constraints are that the joint strength should be at least equal to the strength of the material that you are welding. If you are depositing a layer of material, then the deposited material should exhibit strength and mechanical properties superior to that of the base material that you have intended to deposit. So the matching of the properties are really difficult. So during welding or during deposition, we aim for exceeding the properties that is already present in the case of base material. As you can see in this figure, that is, of course, two plates that have been welded by friction stir welding process. And just a minute, I will take out the laser pointer. Yeah. So you can see these are two pieces of metal. They have been joined in the center. And after joining, what has been done is that such types of strips have been machined out after joining, perpendicular to the direction in which welding has been carried out. After taking out the strips in the perpendicular direction, flat tensile test specimens have been created, as you can see in these photographs. These transverse tensile test specimens have been put in a UTM machine and or in a tensile testing machine, and the tensile load has been applied, and these materials or these you can say joint pieces of plates have been fractured in a tensile testing machine. And as you can see from the necked region, in all cases, the welding is taking place away from the region where welding has taken place. So welding is there in the center. It is either breaking at the bottom or it is breaking at the top, but nowhere it is breaking in the middle. The only situation where you see it has been fractured in the center is this particular specimen, but this specimen, there is no welding that has taken place in this region. If no welding is taking place, it is bound to fail in the approximately in the middle of the gauge section. But when welding has been taken place and welded specimens are tested, they are not able to fracture in the center because the central welded region has got higher strength than what is there in the base material. So in comparison to the base material that you have welded, the central portion of the welded region is having higher strength, and therefore the specimens are breaking away from the welded regions. Apart from this requirement of mechanical properties, there is also a requirement that during welding, the nearby base material, that is the nearby regions or surrounding area around the material that is being deposited or they have been added to it, the nearby material should not lose its property, and if at all some changes are taking place, these changes are quite minimal in nature. Lastly, but not least, it is now very much essential that whatever process is used for welding or deposition of the material should be environmental friendly and it should be safe to the welders. Now, these three simple conditions that are there in case of welding or additive manufacturing, they are quite difficult to achieve, and generally most of the processes fail in either one or more than one of these three criteria. Now I will introduce you to another topic that is, you can say, an allied process of welding, that is known as surfacing. So surfacing basically refers to the technique of depositing a layer of material over another material, and that another material on which a layer of material has been deposited can be called as the base material or the substrate material. And this deposition of the material has been done with the aim of obtaining some desired property on the surface which are not intrinsically present in the underlying base material. So we have got a substrate material, as you can see over here, It has got certain properties. These properties are lacking for some applications. So to improve the property, and that too the properties that are required on the surface of the material, another layer of material is deposited, or you can say an additive layer have been placed on top of a substrate material, so that this substrate material's surface becomes deposited with another layer of the material, and this deposited layer of the material has got superior properties. So am I clear up to now? You can always interrupt and ask if you have any question. Any questions from anybody till now? Okay, fine. So this deposition of the material that is done can be done to achieve several objectives. And please remember, this deposition of the material has been done only on the surface of the material, because we cannot deposit the material inside. And since the surface of the material is only getting affected, so the desired change in properties that are expected are related to the surface of the material. So we may be interested in depositing a layer of material such that the top surface. Any doubts? Somebody is trying to say something. Anybody is asking some question, or somebody has unmuted the mic? Okay, I don't know. Okay. So one of the objective of deposition of the material could be to deposit a wear resistant material on a substrate for increasing the component's wear resistance, so that the wear and tear of the component does not take place and it makes the component last longer. If that is the objective of deposition of a layer of material on the substrate, this is known as hard facing. There may be another application where the substrate material is not corrosion resistant and it is by some environmental medium, it is getting corroded. So in such cases, you can deposit another layer of a material such that the material that is deposited is having superior corrosion resistant properties. If that is the case, the objective is to impart corrosion resistance to the material, to the substrate material. Then the same process will now be called as the cladding process. Sometimes when we are joining two dissimilar materials that are not compatible to each other, what is commonly done is that third layer of material is deposited on one of the faces of the material that are to be joined, such that this third material that has been added is compatible with both the dissimilar materials that we are interested in joining. In such case, the process of deposition of the material will be known as buttering process. Similarly, you can simply add layers and layers of material so that either the component whose dimensions has been reduced because of the wear and tear or damage or fracture, the component can be, the dimension of the component could be further corrected, additional material can be added, or you are interested in building a material by layered deposition. Those processes are generally called as build-up processes in the language of welding. Together, hard facing, cladding, build-up, and buttering form a group of processes that are known as surfacing, which is the allied process. So now today the talk is more on one specific type of surfacing operation that is known as cladding. So as I have already informed you cladding is the process of deposition of a metal layer on the component surface with the primary objective to increase its corrosion resistance against some harsh environment. So depending on the environment in which that product or component has to be used, another material is chosen and that is deposited on top of the substrate material, and this process is known as cladding. The cladding material that has been added on the top of the component, this acts as a barrier between the substrate and the corrosive environment. So whatever corrosive environment is there, it is not coming in contact with the substrate material. Rather, the corrosive environment is coming in contact with the clad material that has been deposited, and already that clad material has been suitably chosen so that it offers corrosion resistance. This cladding that has been done can be performed in two specific thicknesses. One is known as a thin cladding, or it is also known as film coating. Generally, this thin cladding has got a thickness of less than 1 millimeter, or it should be, generally it is of few micron thickness. The thickness of the coating is very small. Maximum it can go up to what is 1000 micron or 1 millimeters. The common methods of depositing thin films or thin film coating are electroplating, which is a very traditional process, chemical vapor deposition technique or CVD, and physical vapor deposition technique or known as PVD. So these are some of the common methods by which cladding of thin layers can be done on top of a substrate. Thick cladding, which consists of depositing a layer of a corrosion resistant material that is definitely more than 1 millimeter in thickness and go up to several millimeters in thickness, are done by the welding processes. That includes arc welding and other processes included. And there are certain constraints in cladding. The most important constraint is that the clad material or the material that has been chosen to be deposited in a substrate material may have different properties. There may be a huge difference in their thermal, physical, and metallurgical properties, causing difficulties in the process. When two materials are combined, they are at a high temperature, they are cooling down, they are coming to the room temperature, they are shrinking to different extents depending on their coefficient of thermal expansion. This may create interfacial stress, and this property can lead to, you can say, peeling off of the coating on the top of the substrate. Apart from that, metallurgically also many materials are not compatible. If those materials are added together, then their phase diagram or their equilibrium diagram will clearly show you that if these materials are brought in contact, particularly in the liquid state, and then they are solidified, instead of forming alloys with good properties, they may form intermetallic compounds, which may be very brittle in nature. They may form phases that are very brittle in nature. So these metallurgical property changes can also create problems. Cost is also another major constraint, because some of the processes, particularly like physical vapor deposition and chemical vapor deposition, they are very expensive processes. And most importantly, the cladding process, when it has been carried out, should not alter the performance of the component. That is, by the operation of cladding, it should not happen that the underlying substrate material should lose its mechanical property or some of its useful properties, which makes the performance of the component in field, you can say, poor. So various methods of cladding or surfacing can be used, and that includes the fusion welding processes and solid state welding process. Like in this figure, you can see gas metal arc welding has been used to deposit a layer of copper on top of the mild steel substrate. I will discuss that in more detail in the subsequent slides. So currently, the processes that are being used in industries are these. One that is very popularly used is what is known as gas metal arc welding or arc welding processes. You can also use popularly what is also used is the submerged arc cladding process. Gas tungsten arc welding can also be used as a process, although you need an additional filler wire to be fed in the arc that is formed between the tungsten electrode and the substrate. Laser-based cladding is another very popular process that is coming up, and it has got the capacity of producing narrower heat affected zone, and several advantages are there. However, the cost of the equipment is expensive, and running of the equipment also requires good amount of expertise and investment. Among solid state welding process, what has been already done or what is being has already been used is the process known as explosive cladding. Sometimes this is also known as explosive welding, where there is a substrate you can see over here, and then at some angle or at some standoff distance, another layer of material is placed. That material is the clad material that has to be deposited, and on top of that, there is a layer of explosive that is placed, which is detonated. When the explosive detonates, a very high velocity is imparted to the plate, that is the clad plate that is kept below the explosive. They will move at a very high velocity, and they will impinge at that high velocity on the metal substrate that is present. This jetting action that basically creates interlocking of the clad layer with the substrate material. But this process of explosive cladding requires special care because high amount of explosive have to be burned. So there are safety concerns. If the material is not very ductile, particularly the clad material or even the substrate material, then also because of the impact of the plate, there will be cracks that can be developed. So this also suffers certain limitations. Therefore, we explored for other processes, particularly friction stir welding for the cladding operations. So one of the first attempt that we did was that we tried to clad a layer of copper on mild steel substrate. Now remember, copper and iron, they don't really mix well. Metallurgically, they are not very compatible. And if they are tried to be joined, several problems can occur. So we tried with the process of gas metal arc welding, where a spool of copper was taken, and that spool of copper was run through the GMAW torch, and an arc was initiated there at the end of copper, and such layers of materials were attempted in the first attempt so that we could optimize the process parameters. Now remember, copper has got a very different electrical conductivity. Thermal properties are also very different. Producing an arc and the formation of the droplets in the case of arc welding of copper is also something which was new, but we could establish the process, develop beads of desired profile, as you can see in some of these figures, and then subsequently several beads were placed one against the other, or one next to the other, like this. So when we were using carbon dioxide as the shielding gas, then a lot of spatters were coming. So a lot of spattering was coming because CO2 was used as shielding gas. When argon was used as a shielding gas, there was a serious problem of arc stability. The arc was getting extinguished. So therefore, some specific composition of shielding gas consisting of argon and CO2 was supplied, and to some extent, with little less amount of spattering, we could deposit several layers of, or you can say several intersecting layers of copper on top of the substrate, so that the substrate of mild steel could be completely covered with a layer of copper. This is the photograph of that, and the plates were cast to look at the inner cross section, and as you can see over here, one complete layer of copper has formed on the top of the mild steel substrate, but there are some issues, some problems that we are going to discuss. Although this is not very clear in these photographs, but still, when we cut the specimen and molded it and we looked at the cross section of it, we found that although on the top the copper seems to be well and nicely deposited, but there were a lot of porosities that were observed in the just below the surface of the cladded copper. Now these porosities that are present, they will act as stress risers. Some of the porosities are open to the surface. Aesthetic of the material was also getting affected. So this porous layer of copper was something which was not very much desirable. So as you can see in this photograph, what was done is that we thought of why not incorporate our friction stir welding process and improve upon these problems of that has been caused by arc welding or gas metal arc welding process. So what we did is that this layer, that previous layer that I have seen over here, this such plate was prepared where a layer of copper was deposited on mild steel, and then the top surface was milled down to some extent so that this surface become flat. If there was no problem, there were no porosity, then after milling, this copper cladded plate would be ready for any application. But as you can see over here, there are a lot of porosities which were further exposed when the surface was made plain. So what we did is that we took this cladded plate, put it in a friction stir welding machine, and made a friction stir welding pass on the plate that has been cladded with the copper. And this friction stir welding pass that was made on this resulted in removal of most of the porosities. The aesthetics of the plate improved, as you can see over here. It's a very nice and completely filled plate. And most importantly, when we cut the cross section like this and looked at the cross section, so in the region where friction stir processing has been carried out on the copper, there were hardly any porosity. So this operation of friction stir processing completely removed the porosity that has been caused when gas metal arc welding was created. Of course, for the comparison purpose, there is a nearby region where GMAW process has only taken place, and you can see some porosities still present, and many of those porosities are very large in size. So this was first solution that we offered, that is after the layer of a substrate of after a layer of a clad material is deposited on the substrate, we can always perform friction stir processing to remove the defects that has been created because of the deposition of the material by conventional process. Later, we moved on to a new set of an experiment where what we wanted to do was to ensure that we would eliminate the arc welding process completely. There were several problems with arc welding process I have already mentioned, and it required that some amount of processing was to be carried out. So we worked on a second idea of what is known as friction stir based surfacing processes. Earlier, it was an arc welding based surfacing operations. So friction stir surfacing is very similar to friction stir welding. You all must be aware of friction stir welding process, which is a process of solid state joining of the material. We take a non-consumable tool with a shoulder and a pin. The pin is inserted in the plate which has to be welded, and the shoulder and the pin are rotated against the material that has to be welded. The frictional rubbing of the pin and the shoulder against the material generates a lot of frictional heat. This frictional heat causes the material to become hot and soft, but the heat is not increased to the extent that melting of the material takes place. After that, the tool is traversed perpendicular to the axis of the joint in this figure, either towards me or away from the screen or inside the screen. In the case of friction stir surfacing, as the name suggests, we are only interested in changing the properties of the surface of the material. So what we do is that we take a tool where the pin length is very short. The pin length is only equal to the thickness of the surface of the material that has to be accepted. So the pin is shorter in length than the workpiece. Correspondingly, the thickness of the surface layer can be modified depending on the thickness of the depending on the length of the pin that we have chosen. There are several similarities. The same setup and tool that have been used can be used for surfacing also, although with the change that the tool design has to be changed, the pin has to be made shorter in length. Just like friction stir welding, thermomechanical processing also takes place. Good amount of stirring of the material in solid state take place, and therefore there is sufficient amount of grain refinement and the properties of the material improve. But remember, this surfacing has to be done on this entire top surface of the plate. So the entire plate has to be surfaced. If we are just doing one friction stir processing pass, then only this portion of the material will get joined, or this portion of the material will get the surfaced operation. So what you have to do is that several such passes of friction stir processing has to be carried out with some amount of interface. So as I am doing these passes, you can see more and more area of the plate is getting processed, and then we can cover the entire plate with several friction stir processing passes. And if the need required, we can remove the portion where the pin has been withdrawn because there is an inherent hold present. And if required, we can also do some machining to obtain a layer of material that is completely covered with another layer of material. So to test our experiment, to test our idea, this type of friction stir cladding experiments were carried out. So in this method, what we did is that we took two different substrates. One was an aluminum substrate, another was a mild steel substrate. In both cases, we tried to clad a layer of copper on this substrate. Now I must again mention that the copper as a material has got problem of compatibility both with mild steel and aluminum. So deliberately we chose the combination of material such that with conventional fusion welding processes, it was not possible to get good quality of clad layer. So in both cases, what was taken is that the layer of or a plate of substrate was kept, as you can see on this in this schematic. On top of it, another plate, which is visible in this figure also, of copper was taken. They were firmly clamped in a friction stir welding machine. A friction stir welding tool with a shoulder and a pin was taken, and then one layer of yeah. Any doubts?
Participant, please mute your mic. Participant.
వాడికి యాక్చువల్ గా అది కాదు లీవ్.
Sir, you can continue.
Okay. Somebody forgot to unmute.
Yes,
No problem. Okay. So in this case, one friction stir welding pass was carried out, and certain case was taken as you.
Sir, your mic is off, sir. Your mic, sir.
Now am I audible?
Yes, now you're audible, sir.
Oh, I think administrator muted everybody, that included me also. So, okay, so good. Coming back to my presentation. So in this particular case, we tried to deposit a layer of or bond a layer of copper on the mild steel and aluminum substrate. We took the two clamped it in a friction stir welding machine and took a tool with a pin length which was just slightly more than the thickness of the clad layer. If the pin thickness or the pin length was much smaller than the clad material, then only the clad material would have stirred and no bonding between the clad material and the substrate would have taken place. On the either side, if the pin length was excessively high, then during the friction stir processing, the substrate material, which was mild steel or aluminum, would have stirred and come to the top of the clad material, mixed with the clad material even at the top surface, and therefore whatever was our permanent inherent objective, that would have not been achieved, because we wanted to keep the substrate material inside and to ensure that no contact takes place between the substrate material and this. So after several trial runs, we could decide what should be the length of the pin that has to be used. Setting of the process parameter was another problem. So as you might be aware, that friction stir welding process requires several process parameter has to be set. That includes the tool RPM, the speed at which the tool has to be traversed, the tilt angle, because the tool is not vertical to the axis to the plane of the plate, rather it is tilted on the side which is opposite to the side in which you are moving the tool. So if you are moving the tool from left to right, the tool will be slightly tilted on the right side. So we had no previous experience of this, so we tried a range of process parameters, and there were some failures that has to be that helped us in gaining the insight into the material. So one of the problem was that when the tool RPM was very high, like 1000 RPM, and a large tool plunge was there, then the temperature was excessive and the substrate, which was aluminum, actually melted and it started to flow out like this, and a complete disaster was created, as you can see in this figure. Similarly, when the tool tilt was 0.5 degrees or 1 degree, then this type of a tunnel defect was created, and this is also a complete failure. However, when the RPM was set to a lower value and the tool tilt was kept at 1.5 degrees, then the two materials could, the copper could be cladded on the steel. And of course, there were other one very other important process parameter that had to be set, and that was the tool plunge. So if the tool plunge was less, then the shoulder was not completely coming in contact. Whereas when the tool plunge was excessive, then this type of flash were coming out, which were making this unacceptable. But however, after several trial runs, we could fix the parameters. Tool RPM, as I told you, 1000 was giving excessive heat. So at 700 RPM, 100 millimeter per minute, 1.5 tool tilt, 20 mm shoulder diameter, 6.5 mm pin diameter, and pin length of 3.5 worked well, because of the thickness of the plate, that thickness of the clad layer that we have deposited was 3 mm. Now, as I have mentioned earlier, when we are performing this cladding operation, then in one pass, only a certain portion of the material could be cladded. Like this is a plate of mild steel, and there is a copper on top of it. And if one pass is there, then only from here to here, up to this width only, some amount of bonding has taken place between the copper and the substrate. Whereas the remaining portion has not been bonded. So therefore, there is another parameter that has to be set, which is not required in the case of welding, but here it is very much required. That is the tool offset for the subsequent passes. So if one pass is made, then for the second pass, the tool has to be moved in the left or right direction. So to estimate as to what should be the amount by which the tool has to be moved or offset, we made this simple schematic diagram, and we can to guess this thing. Whenever one pass of cladding is carried out, the material get processed and recrystallized in this parabolic zone. So this parabolic zone will be having a width equal to the tool shoulder, and at the very other extreme it is having a width equal to 0, and at the point where the substrate and the clad layer are in contact, this is the width up to which bonding has taken place. Whereas the region of the material of the clad and substrate which are outside this parabolic region, they have not joined. So if we have to offset the tool, and if the offset is for a very large distance or a distance larger than what maximum possible has been shown in this schematic, then there will be an unbonded region remaining over here. This unbonded region, if it is created, this will lead to peeling off of the clad layer, and therefore the maximum amount of offset can be kept equal to only this. Now, why we want to keep the maximum tool offset was that if there is a plate of 10 millimeters and the offset is every time 2.5 millimeters, then it will require at least 4 passes. But if the plate is of same thickness and we are giving only 1 mm offset, then you have to go for probably 5 or 6 passes. So therefore, to minimize the effort of friction stir processing passes, the maximum possible tool offset is what is desired. And after making this calculation, here also you can see in this pass, if the offset is too much, then there is an unbonded region created over here. And if it is too less, then unnecessarily effort has to be there. So what we did is that we tried with several experiments. That is, the tool offset was kept as 6 mm, 8 mm, 10 mm, and 12 mm. And we then performed X-ray radiography to serve two purposes. So after cladding these plates with offset distance or different offset distances, the entire copper cladded plate was sent for X-ray radiography, and X-ray radiography revealed this result. You can see the photographs, and as you can see over here in this portion, the tungsten carbide tool has actually broken down because of some reason, some intermetallic formation or whatever has happened, and this is stuck up, and this is again a failure. Similarly, the debris of the tool, that is tungsten carbide tool, which was chosen for this experiment, is also stucking up, and is also causing problem. The other radiograph, you can see this is not having any flaw, this is not having any defect, but as you can see over here, the offset distance was slightly more, so there is an unbonded region between the two passes. So in this way, we could optimize the offset distance, and we could produce the friction stir welding passes. This is the macrograph and a micrograph of the cladded layer. So several passes with the 7 mm tool offset was produced. And as you can see, this is a substrate. On top of it is copper. During friction stir welding process, you can see there is a interlocking that is taking place. Of course, there is metallurgical bond as well as interlocking that has taken place between the substrate and the clad material. And this interlocking further enhanced the strength that was achieved by the metallurgical bonding. At a magnified level, you can see that such integrate bonding or mechanical locking has taken place between the substrate and the clad material, ensuring that the clad material is firmly anchored on the top of the substrate material. Second important thing that you will be noticing over here is that your base material is having certain grain size, as you can see from the micrograph, but after the cladding has been carried out and stirring of the material has taken place, the substrate material has also become very fine. So there is no grain coarsening that has occurred in any of these situations. So two important things can be seen from this. One, there is mechanical interlocking, there is metallurgical bonding that has taken place, and there is grain refinement that has taken place in the substrate material. So if the grain of the substrate material have become finer, that means the mechanical property of the substrate has also improved a little. So this can be clearly seen in this material. The process parameters were so ideally chosen that there was a very good intermixing that has taken place between the substrate material and the clad material, and the stirring of the material was really good. After that, mechanical tests were carried out. So from the cladded layer, what we did is that tensile test specimens were machined out by iridium machine, and you can see. So once these specimens have been carried out, and if you look at the cross section of it, there is a copper layer on the top and a substrate at the bottom. Similarly, other specimens were also created only from the substrate and only from the copper, just to compare and see how they are behaving properly. Then extensive micro hardness testing was also carried out, because micro hardness testing was carried out as per the scheme shown in this figure. So what we did is that on the cross section of the specimen that has been cladded, it was molded and nicely bound, and then indentations were made just below the clad layer, at the interface of the clad and at the interface of the substrate and clad, and near to the top of the clad layer. Similarly, indentations were also made across it, right, starting from the very top of the clad layer, going through the clad layer, coming to the substrate, and very end of the substrate. Similarly, more micro hardness was carried out on the base copper. Then micro hardness was carried out on the top surface of the copper plated, and then another set of micro hardness was taken after removing the top 1.5 millimeter layer of the clad surface. Several indentations were taken and the hardnesses were reported. Similarly, there is a one very important mechanical test that has to be done, and that is to see whether the clad and the substrate materials are peeling off, and that test is known as a bend test. So three type of bend tests were carried out. That is, three specimens were taken out from the cladded layers. In one case, the bend was carried out such that, as you can see in this figure, the clad layer is at the bottom, the substrate layer is on the top, a plunger is kept, and a U bend test was carried out, so that the maximum deformation is there in the cladded material, less deformation is there in the substrate material. Next set of bending was carried out, where the substrate material was at the bottom, the clad layer was at the top, and when the plunger was moving down, there was maximum deformation in the substrate layer and less deformation in the clad layer. In fact, the clad layer was subjected to compression. And the third test was that this specimen was kept perpendicular to this, and it was deformed so that, the clad layer and the substrate were deforming together. This is the result of the bend test, and as you can see, this is the face bend test, this is the root bend test, this is the side bend test. So this was deformed like this, and like this, and in all cases there is no peeling off or no separation of the plates that has been created. This is the starting specimen, and this is what we get at the end. Yeah. So before I go, I'll just, this is the result of the tensile test specimen that was tested. As I have mentioned, we have prepared three types of specimen. One made up of pure copper. This is the stress strain diagram of that. This is the stress strain diagram of the mild steel substrate. As you can see, it has got higher strength than what is obtained in the case of pure copper. And then this is the stress strain diagram that we obtain when the copper cladded steel was tested. And all those three are compared over here. This is the stress strain diagram of copper. This is the stress strain diagram of mild steel, and this is the stress strain diagram that we get of copper cladded steel, as you can see. So the middle one is the one which we are getting. So this material that has been cladded with copper is also performing very well, and since it is made up of copper and steel, so its properties are also in between them. So that means this process of cladding has not led to any deterioration of the mechanical properties, but rather the mechanical properties have remained as such. This is the SEM analysis or SEM images and mapped EDEX images of the copper cladded steel. As you can see over here, there is a very clear interface between a clean interface has been formed between the mild steel and copper. Mechanical interlocking that I have mentioned over here, it is also present, and these even at a magnified image are having a hook type of a structure. The interface is very clean, no intermetallic is at least visually observed, and more interlocking is visible in these SEM images. Then we did the EDS analysis to see what are the elements present, and at the interface you can see that almost equal percentage of copper and iron are present, because copper was of course pure copper, and the substrate was mild steel, which is also mostly having copper. And as we move from the interface to the region which is slightly on the copper side, the extent of copper is increasing, the atomic percentage of copper is increasing, and the atomic percent of iron is decreasing. Then we performed mapped EDEX, as you can see in the top figures. In the mapped EDEX, what we did is that we tested as to what are the spots from which we are getting peaks of copper. So we can see that the copper peaks are only obtained from the region that is seen in the macro graph as copper, whereas iron is seen only in this. So no iron peaks are obtained in the clad portion. That clearly indicates that iron has not been able to travel and move to the clad region. Now, this is very significant in the sense that if we are performing we are performing cladding by other processes like laser beam cladding, or we are performing arc-based cladding processes, there is a very good amount of mixing taking place of the substrate and the clad material. So if this type of image is taken out, this mapped EDEX is taken out from laser cladded specimen, what we expect is that there will be a good amount of iron in the cladded region and good amount of copper in this region. So your top cladded layer will not be free of iron. That was what was desired in the case of cladding operation. We didn't want any substrate material. So in all those fusion welding or fusion cladding processes, this cannot be achieved. This I have already shown. This is the more details of the tensile test specimen. As you can see, the base steel has got a UTS of 462. The base copper has got UTS of 227, and our copper cladded steel has got a UTS of 359, which is very close to what was there in the case of steel, and it is very much in between the strength that is obtained in pure copper and steel. Similarly, the yield strength is also lying in between. The yield strength of pure copper is 131. The yield strength of base steel is 326, and the combined yield strength of is 261, which is more than that of the clad copper, but slightly less than that of the steel. As far as the elongation is concerned, it is slightly less. And you can see the combined elongation that we are getting is slightly less than what is obtained in the case of mild steel. These are the factographs where you can see there are clear dimples present, and these two regions have remained intact even up to the point of the fracture. So whenever the fracture is taking place, these two regions are not getting separated. This is more visible in the case of this magnified image of the tensile test specimen. So as you can see, the tensile test specimen is fractured at this point, but when elongation is taking place or when yielding is taking place, the two different materials are yielding together, but they are not separating out. And these type of perpendicular voids are created even at the under the SEM also we can see these type of voids that are present, and these material has not separated out. When we performed EDS also of it, we found that this region was completely copper, this was steel. So no intermixing has taken place, and these voids that has been created, they are also partly on the copper side and partly on the mild steel side. So very good interlocking of these two have taken place that can be proved. This is the result of the bend test that I have described, and you can see over here the material that in all the face bend, root bend, and side bend, it could be bent into almost an 180-degree bend. Of course, before it being formed into 180-degree bend, it slipped out of it. So this is the extent of almost 160-degree of bend has been created, and they are even after bending, the copper and steel are inseparable. They are still remaining intact. So as a conclusion, we can say that friction stir cladding process can successfully produce cladded samples with copper bonding between copper and clad copper with mild steel substrate. Tungsten carbide tool material with low cobalt binder was found to be more suitable for the steel cladding operation. Process parameters for successfully cladding was found to be 700 RPM and 100 millimeters per minute. Grain refinement along the steel region was seen with an average grain size of 5 microns, while copper showed slight coarsening. Cladding suggests cross-boundary metal transfer near the interface, but radiography proves that the cladding specimen does not contain any flaw or defect. Mechanical properties of the cladded sample falls in between that of the base copper and base steel. Factography revealed no peeling was observed and the clad flake as a single material, and bent edge confirmed no signs of crack initiation, delamination, or micro crack along the convex surface. So thank you all. That's all from my side. Now I will take up the question answers.
Hello, sir.
Yes.
Myself, Dr. Manish, working
Yes.
as assistant professor in CPET Jaipur in mechanical department.
Okay.
Sir, you have shown the vending test. That vending test was gradual or impact. Have you gone for impact vending test also?
No, it was a gradual test. So at a low value of strain rate, the material was deformed so that it converted into a U shape and passed through it. So it was not an impact test that was carried out over here. So the main objective was here, what we want to see, we have got a layer of copper that has got very high ductility. Its deformation behavior is completely different to that of the steel. So we wanted to see when more amount of copper is getting deformed, whether it is peeling off or not. So this test, that is the bend test that is carried out, this was primarily to see whether in the case of extreme bending, when a lot of plastic deformation is given, whether the clad and the substrate layer are peeling off or any cracking has happened. So we found that nothing has happened. The peeling has not taken place. That is one thing that is quite successful. And second most important thing is that if any brittle intermetallic may have formed, then cracking of the substrate or the cracking of the at the interface would have taken place. So in both cases, this was not taken place. I hope I am clear.
Yes, sir. One more question.
Yes.
While using friction clad welding, and what will be the optimum rotational speed and tool diameter, which is giving better result?
So in our case, we did several trial runs, and one of the idea of the process parameters I will give, it is there in the PPT also. So for this cladding operation, we use this parameter. Tool RPM was 700 RPM, tool speed was 100 millimeters per minute, tool tilt was 1.5 degrees, shoulder diameter of the tool that we have chosen was 20 millimeters, the pin diameter was 6.5 millimeters, the pin length was 3.5. The shape of the pin was in the shape of a truncated cone. There was no thread marks or any type of marks that were made on the pin. The tool material was a tungsten carbide tool with approximately 7 to 10% of the binders. So it is a ceramic based tungsten carbide tool. And as you know, ceramic based tools will, when they are being fabricated, some amount of binder is put. So cobalt was used as a binder, and with this cobalt binder, which was approximately 7 to 10%, the tungsten carbide particles were held together, the tools was created. We bought these tools in form of cylindrical rods, and the shape of the pin and the length of the pin and everything was created with us in our own lab.
The tool was of which material?
The tool was made up of tungsten carbide. So tungsten carbide, basically tungsten carbide is a ceramic material. It is very brittle in nature. And this tungsten carbide, I can show you something also. Have So this is, you can see my camera. This is how tungsten carbide looks like. It is a very brittle material. If I just drop it, it will break into pieces. So this was having fine grains of approximately 8 to 10 micrometer grain size of tungsten carbide, and this was firmly bonded with some binder, and the binder that was used in our tool was cobalt, and the percentage of cobalt was approximately 7 to 10%. With different materials, with different vendors, we obtained different, but 7 to 10% was working fine. And the material of the binder was cobalt, and the tool was mostly having tungsten carbide.
Thank you, sir. Thank you very much. I request you to share the slide with all of the participants. It will be very insightful to us.
Yeah, I can talk to Professor Zubair, and we'll see how we can pass it on to you. Probably handouts we can share.
Okay, sir. Thank you, sir.
You're welcome. And I would encourage all of you to, whenever you need to use some of the facilities, you can send your students. If you have got some good MTech students, you can ask them to come and join PhD with our group. So we are open for that also. We are looking for good PhD scholars. And mostly we do experimental work. We do some simulation work also, but mostly it is experimental. Most of the experimental
Sir, sir.
Yes.
Will you share the contact detail with us?
Can you repeat your question?
Sir, I request to share the contact details, your mobile number.
Yeah. So you can just remember my name. My name is Mohammad Zahir Khan, and I am in IIT BHU. So if you Google Mohammad Zahir Khan IIT BHU, you will get my mobile number also, email address also. I'm sorry I could not put it in the slide. I should have done it. So my mobile number My mobile number also has a WhatsApp facility. So that is also there. My email address is also there on the website. So you can just look into it. Just remember my name, Mohammad Zahir Khan, and IIT BHU. Just Google it, automatically it will go to my homepage and you can note my number. Okay.
Okay, thank you, sir.
Thank you. So other questions?
Dr. Zubair sir, Zahid Khan sir.
Yes. Yeah, please ask your question.
Dr. Ahrad, you can ask. You can unmute and you can ask.
Okay, let him come. Sir, good evening, sir. This is
Good evening.
Preetham, Dr. Preetham.
Yeah.
So one small question is there.
Yeah.
How do welding process parameters specifically, that heat input and welding speed and all this gas composition influences that parameters?
You mean to say in the arc welding processes?
No, sir, in the
Friction
welding
stir.
processes. Yes, friction welding. Yes, sir.
In the case of friction stir welding, we didn't use any shielding gas, so that is not a parameter. But the important parameters are the tool RPM and the tool welding speed, the tool speed at which it is moving in the linear direction. So the
Okay.
ratio of the RPM to the speed, that is the most important parameter that decides the heat. If the RPM by speed ratio is very high, the heat input is very high. If the RPM by speed ratio is low, that is one parameter. Second parameter is the tool shoulder diameter. If the tool shoulder diameter is high, then also more heat input is more heat is generated. And the third parameter is, of course, to some extent we can play. Generally, we don't play with the machine that we are having. That is the amount of Z thrust that has been put. So if the Z thrust is high, then again more heat input can be liberated. But generally we use the machine that we are having in the position control mode. So we did not experiment with that.
Okay. So in this, what are the things we have shown? Can we able to use the FEA models in this kind of experimental work?
Definitely, we have done some work. We have done the heat generation model, the materials flow model that we have done. Some MTech work has been already done in this area. Apart from that, we have also used just as I have mentioned that the defects that are there, the grain size and all those things are there. So we have also done some work with some of the BTech students where we predicted the grain size based on the process parameter, particularly by using machine learning algorithms. So we performed several experiments, not with this cladding experiment, but they were welding experiments. And then we generated several microstructures that we are getting. The grain size were calculated, and then with the process parameters, what grain size were there, then machine learning algorithms were used to predict that with which parameters or what type of grains we are expecting. So that type of work also we have done.
Specifically for this kind of like experimental work, what you have done, can you use like we can use COMSOL or like ANSYS?
Yeah.
Is it applicable for this work?
Yeah, COMSOL will be useful because as you know that the material properties significantly change. We are reaching to a temperature which is very close to the melting point. We don't melt the material, but it is very close to the melting point. So that multi-physics that is there in the COMSOL that comes in handy, and that has to be used.
Okay, sir. Okay, sir. Thank you.
Thank you.
I think one more participant who is raised her. Sai
Yes.
Somesthi, you can ask question.
Good evening, sir.
Good evening.
Sir, what are the factors that you have considered to optimize the diameter and the speed of the tool, sir?
So in this particular cladding experiment, we have relied mostly on trial and error. So when the tool shoulder diameter and the RPM were very high, then the melting of the substrate took place when we were welding aluminum. When we are welding depositing copper on the steel substrate, and when again the heat input was very high, then there were some chances of the substrate, the clad material reaching almost to the melting point. And this melting, any type of melting that is taking place either in the interface or in the clad position or in the substrate, this is completely disastrous. So we started with this 3 set of experiments where the diameters of 15 mm, 18 mm, and 20 mm were taken. Similarly, the RPMs were varied from a very high RPM of 1000 RPM to we went down to like 500 RPM, and we found that at an RPM of 700, when the shoulder diameter was 20, was giving sufficient results. The diameter of the tool was also kept on the higher side because, as I have mentioned in my presentation, that the tool that has to be traversed during the friction stir processing operation, that has to cover the entire plate. So if the tool shoulder diameter is very small, then we have to make very large number of passes so that the entire plate could be covered. Whereas if the shoulder diameter is very small, then we have to make very large number of passes. So therefore, the tool shoulder diameter of 20 mm was chosen. If the tool shoulder diameter was more than 20 mm, then again the amount of heat generated was very large, and that could lead to two problems. One is, of course, a very disastrous problem where the substrate itself melts in the case of aluminum, or this high heat input can lead to grain growth in the case of the clad layer, that is copper. So the clad layer of copper, even if the optimized parameter, was also experiencing very small amount of grain growth. But if the shoulder diameter was still large, then it could have caused the grains in the copper, because of the excess heat, it would have grown in size. And with the large grain obtained in the copper, as per the Hall-Patch equation, the strength of the clad layer would have gone tremendously down, and therefore, although it could have sustained or they would not have any effect as far as the corrosion resistance is concerned, but it could have a very disastrous effect as far as its service life is concerned, particularly against wear, tear, and such conditions. So therefore, the shoulder diameter was kept around 20.
Thank you, sir.
Participant, if you're having any question, you can ask. Session is open.
Anybody has any question, you can unmute and ask. If you have any other doubts also, apart from what we have discussed, you can also share with us. If anybody is working in the area of welding, joining, additive manufacturing, if you have some doubts, particularly related to any experimentation, you can also share and we can discuss that also.
Sir, I have a small query.
Yes.
Sir, from the heat source modeling point of view, which
Yeah.
heat source is best for the friction stir welding and for cladding also?
We have not actually done that part much. Okay, so the cladding was mostly done in experimental fashion. So I cannot comment, but yes, different approaches have to be used so that you can actually decide which type of heat source can be best model for this process.
Sir, recently I did one small cladding work on 316L using the laser only, that small
Okay.
layer. But the problem is that I'm using it's a
Gaussian?
surface type Gaussian
Okay.
distribution, but I'm not considering volumetric
Okay.
because
Okay.
it's only layer wise. Like normally for heat source, especially for laser, we have to use conical model
Yes.
as a volumetric heat source.
Yes.
So we are trying to combine the double ellipse shadow model and conical with the normal laser welding process. But for cladding, the results are not up to satisfactory mark.
Yeah, because two different materials are involved. They've got different conductivities. So yes, that is true. But I will not be able to help you much because, as I have mentioned, I have not done much of the simulation work on this. Mostly it is on the experimental side. But we can discuss later. You can see.
Audience, if you're having any participant, if you have any question, please ask, or otherwise we'll close in the session.
So I think the audience is also very tired. It is quite late.
Yes, sir. Yes, sir. So thank
So
you,
I think
sir,
we can close.
for attending this 6 days ATAL online FDPs. And thank you again for accepting our request. And I hope all these faculty members are enlightened with your knowledge. And definitely they'll contact you. And we also try to contact you whenever you require. And once more again, thanks to you and all the participants who have spent the time in this late night also. They're joining and listening something. But it is really like appreciable to all these faculty members who were means in the daytime they used to complete their routine work. Again in the evening time they need to listen all this 2 sessions daily. That is really quite difficult and hectic task also. But apart from that, we are thank you to all the participants and thank you especially for you, Dr. Zahir sir. And we all are blessed to have with you us. Thank you, sir.
Thank you very
Okay.
much. It was a very good experience. And I enjoyed giving lecture late in the night, and I was very happy that very good amount of participation is there. I am very happy that
Yes, sir.
many of the participants were so nicely listening that they had so many questions to ask. Generally, at the end of the presentation, I don't get many questions, but yeah, the participations was very good. The participants asked
Yes,
good
sir.
questions.
Actually,
And
we have planned to keep this online FDP during this day session. But we
Okay.
thought maybe we used to also busy with the classwork and other meetings. So many things are there. So same problems will be there maybe for other faculty members. So for purposefully, planningly, we did these things. Like in the evening, if you keep, at least we can hear something, we can listen something in this thing. But anyway, even
No,
we
this is
also feeling
a
tired.
wonderful idea. This is a wonderful idea. In fact, we will also try to replicate it sometimes because not only listening, well, so I'm still sitting in my office, and
Yes,
if
sir.
it
Yes, sir.
was
We can
a
identify.
daytime, it was a daytime, so many students would have been coming, so many calls I may be getting, some student coming with this doubt, that doubt. So
Yes, sir.
even if
Yes,
I'm
sir. Yes,
not
sir.
taking class also, then also there is a lot of distraction. So this is
Distraction will be
also a
there.
wonderful thing that we can sit back and in the night time we can have some lectures. So it was a good and a nice experience for me also. Thank you very
Okay,
much
sir.
for
Thank you.
inviting me. So I'm signing off. Thank you
Thank you,
so
sir.
much.
Thank you.
Thank you, sir.
Thank you so much.
Participant can log out. We are ending closing the session. Thank you all.